Hi mathematicians! In this video, I want to share with you one of my favorite topics from when I was in high school in AP Calculus, and that's the topic of volume. Now, in this year's exam, they did not include the last unit, but I love this topic so much that I want to teach it to you now. So we've learned already that area can be found by taking the integral. The way we did that, remember we started with Riemann sums? So we found the area of each of these rectangles. This is a left Riemann sum. And we used that to approximate the area under the whole curve. So we found the area of each of these rectangles. And then we said if the width, this change in x, this dx, gets really small, it would be like we have just vertical lines, and we would be able to add them up and get the exact area. And that's what we said is the integral. So we found a way of going from one dimension, a line, just the height, the f of x value, to give us 2 dimensions, the area, this whole area. Now we can use a similar concept to go from 2 dimensions to 3 dimensions. So if we start with area, then we can go to volume. So you might still have this handout from when I gave it to you right before we left school. And this shows how we can go from area to volume. So we have this region, and we're going to say out of the region is going to come some shape that we can find the area of. So we can find the area of this rectangle and all these rectangles, and if we add up all these very thin rectangles, it will eventually give us a solid. If we have all these rectangles so close together and so thin, it will give us a solid, and that will give us the volume. So let's do some visualizations of this. So here we have curves, right? And before, we were finding the area by adding up all these lines. So we'd add up the line from here, from here, from here. We add them all up, right? Now we're going to say, for this line, let that be the base of, say, a square. So we have one square that's sticking out from this graph. And if we move it, the size of the square changes based on the height on the bottom on this graph. This height changes the height of the square and the area of the square as well. So if we move it, the square is at different sizes. Right now I only see one shape, but let's make it so I see a few more shapes. Right now there are 5 shapes, 5 squares that are sticking up out of this graph. So I can turn it around and you can see it looks from overhead the same as the graph that we have on the left, but sticking right out of it are the squares. Now if we increase the number of squares we have, we can see a volume, a solid figure starting to emerge. And if we go more and more squares, you can see right now the starting of a shape, of a solid. And if we have as many as possible, it would be a smooth shape. From our squares, we kind of get this funky fish-like shape. Now let's do it with a different shape. Here we have an equilateral triangle that's going to be sticking up. So now we have a triangle that's sticking up out of this shape. And if we increase the number of triangles, and we make it go all the way till the end, you can see a different shape start to emerge. This one's more like a fin that's sticking up like a shark fin. And if we have semicircles, we have one semicircle, a few semicircles. Can you see the shape that this is? And now we have a solid volume. So architects a lot. So in this example, our cross-sections were semicircles, equilateral triangles, or squares. But you can have also more complex cross-sections. So understanding cross-sections is a really key idea if you work in architecture, especially. My sister is an architect, and she constantly has to draw cross-sections of the hospitals that she's working on or the buildings. And here our cross-sections are just squares, but you might have more complex cross-sections. For example, many of you might have gone to One World Trade Center, and this building clearly shows the cross-sections. Each part of this is a separate shape, and that you add it together, you get the whole building. So I want you to work on a project that I gave you a while back, and I'm going to link all the tools to it again. So you remember the foam board that I gave you? So you're going to attach the graph that I gave you to the foam board, and you're going to put in the pins to line them up around each value on the x-axis to create a cross-section that's perpendicular to the x-axis. Then you're going to take the cross-sections, the areas that I have for you, cut them out, and you're going to weave them through your pins. So this is the second cross-section. I missed the first one. But you're going to weave it, so you need at least 3 pins for each cross-section. And you're going to build the areas and there's the second one. And you'll put each of the areas in until you see the whole volume together, from -1 until 2. So your assignment, I want you to create all 3 volumes using a square, using the semicircle, and using the triangle. So you're going to need to submit 3 pictures for me. Once you finish one, have all the squares in it, you'll take the picture, then you'll take them out and show me this next one. I hope you have fun doing this.